Hello everyone, my name is Katie Emilio and I'm an engineer in the Professional Development Department at ACI. I'd like to welcome you to today's webinar, Improve Concrete Performance with Slag Cement. We're glad that you could join us. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 1 PDH. Your certificate will be available in ACI University under the Certificates tab within 2 days. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for 1 learning unit. Today's webinar discusses the use of slag and concrete, and you can see the course description on the screen as well as in your handout. Our learning objectives for this webinar are as shown on the screen, and they are also available in your handout. Now I'd like to introduce our speaker. Professor Doug Hooton is the NSERC CAC Industrial Research Chair in Concrete Durability and Sustainability. His research involves finding ways to reduce the greenhouse gas emissions associated with concrete infrastructure. He investigates the use of materials such as supplementary cementitious materials and ground limestone to produce a stronger and more durable concrete product. His research has informed the specification codes associated with the American Concrete Institute, the Canadian Standards Association, and ASTM standards. And now Doug will begin today's presentation.
So I'm Doug Hooton, as mentioned, and I will be conducting this webinar this afternoon. There we are, finally. Okay. So this talks about slag cement, but in general, slag is one of the supplementary cementitious materials that can be added to replace part of the Portland cement and concrete. And you might ask, why complicate your life? If you're a producer, why add something else into the mix? There's a whole bunch of technical reasons for this, and there's also some environmental reasons for doing this. And some of these things may be beyond where you want to get to, but Portland cement, when it hydrates calcium silicate hydrates, which produces that, which bonds the aggregates together and produces the strength of concrete. But as a result, there's also this byproduct calcium hydroxide that doesn't provide much in the way of strength. So the slag and the other SEMs will combine with some of that leftover calcium hydroxide and produce more calcium silicate hydrates, reducing porosity and improving properties. It also, the SEMs have an impact on densifying what are called interfacial transition zones around aggregate particles. There's usually a weak zone around every aggregate particle where there was water originally in the mixing when the concrete was fresh, and the cement grains can't pack up against the aggregate grains very closely. And the secondary reaction of these supplementary cementitious materials will densify this zone and help to better develop the strength of the aggregate and reduce the permeability along these pathways. It also, SEMs, many of them will reduce the alkalis that are in the pore water. The pore water in concrete is typically pH 13 to 14. And it will bind up some of those alkalis and in the calcium silicate hydrates and help prevent alkali-silica reaction. It will also increase binding of chloride ions that are in the water, penetrating through, so they become bound and they don't make it to the reinforcing steel to cause corrosion. They can also improve sulfate resistance for a number of reasons, including using up the calcium hydroxide and reducing the permeability of the concrete. Often materials, when used in the right quantities, such as slag, also reduce the heat of hydration, which reduces thermal gradients and temperatures in the concrete. It can reduce the potential for thermal cracking. Also, because you're replacing Portland cement, which is the most energy intensive and CO2 intensive part of the concrete, you're reducing that environmental footprint of the concrete by reducing the amount of clinker in the concrete. So ACI has this document 233R, which is Guide to the Use of Slag Cement in Concrete and Mortar. And it addresses the use of slag cement as a separate cementitious material added at the ready mix plant or precast plant with Portland cement in the production of concrete. It doesn't deal with other types of slags from other non-ferrous slags, and it deals with recommendations for use of this material. The term used in ACI, so I'll go back briefly, is slag cement. It's also used in ASTM. In large parts of the world, ground granulated blast furnace slag is called GGBFS. So it's the same material, but here in North America it's been coined slag cement because it is somewhat cementitious on its own, although it's not typically strong enough on its own to be used without some Portland cement. So slag comes from iron blast furnaces, and iron is produced by mixing iron ore, which has iron oxide in it, up in the upper left, with impurities in it, typically silica and alumina. And they flux it to try and reduce the temperature at which it can separate the iron from the other materials in the ore, using typically a limestone or dolomite, or a combination rock. And so that goes into the furnace along with coke, which is just heat-treated coal, which gives it higher energy. And what happens in the blast furnace is, as it gets hot and there's air blasting through this thing, the iron comes separate as a liquid iron, and because it's denser, it falls to the bottom. The slag, which collects all the impurities from the ore as well as the fluxing stone, floats on top, and the burden is just the uncombined material that hasn't fully completed that. So what they do is they tap off the furnace. The iron's tapped off every couple of hours and goes to a steel making furnace to turn the iron into steel, and the slag is tapped off separately, the liquid slag. And it can be treated in different ways. It can be just dumped on the ground, air cooled, and it can be broken up for use as aggregate. It can be slightly expanded to make a lightweight aggregate, or it can be granulated to make a glassy material, which is what we get a supplementary cementitious material. This is a schematic of a blast furnace, and they're blasting hot air into the thing around these toyers around the edge. The molten materials towards the bottom. There's a series of gates which introduce all the materials and control the oxygen in the furnace. So it's a continuous process in terms of the materials feeding down, but the liquid materials tapped off intermittently as there's enough material to remove. So if the molten slag, it's coming out at about 1500 degrees Celsius. If it's quenched rapidly, it becomes so viscous and solidifies into a solid, it doesn't have time to form crystals. It becomes a glass or amorphous material. And it has to get down to below about 800 degrees for that to be sufficiently viscous that it doesn't form crystals later. The composition of slag is such that it would like to become crystals, which would make it non-reactive, but the rapid quenching in water allows it to become a glass. So again, there's a picture of a blast furnace on the left, and there's a couple of stacks which are from the stacks from the granulator units, which are down below. And on the upper right, you see the blast furnace, and they're tapping off the slag out of the furnace there into a runner, and it comes down the runner, and then it's fed in the lower right into a stream of water, and that's where it gets granulated. It goes from 1500 degrees down to almost room temperature in a few seconds. And so that material, there's a schematic of a granulator, a typical granulator, there's different types. And so the slag goes into this spray of water, and then it's filtered out. It goes into a tank where the slag is removed, and some of the gas that's formed from the steam that's generated, because there's some H2S in the material, they hose it, they use water sprays to control the air emissions. So the granulated slag looks like sand, like a coarse sand of that color. And then you take that material, it has to be dried because there's some moisture in it from the granulation process. And then it's ground, typically in ball mills or maybe a vertical roller mill, and ground to a powder to cement fineness before it's used. So you get this nice white powder. Now, even though slag is a byproduct of making iron, it's not uncontrolled. The chemical composition of a slag from a given blast furnace has to be controlled because it's the chemistry of the slag. They monitor the chemistry of the slag before they tap the furnace because that controls the chemistry of the iron that they're trying to produce. So the slag has to be in the right range before they have the right purity of the iron that they're making. So the slag chemistry has to be consistent for a given furnace where they have, standard raw the ore from a certain source and the flux is from a certain source. And so the chemistry is controlled. The granulation process controls the glass content, so it's almost all glass, typically above 90%. The slag cement producer then takes the granulated slag and grinds it, and they can control the activity by grinding it to different finenesses to control the development of strength. They may add some calcium sulfate or gypsum, maybe underground, depending on slag composition, to balance the material. So the 233R has different chapters in it. The first part is on, chapter 3 is on properties and product types, and I'll talk a bit about that. I won't talk about storage and handling. It's typically, handling with slag cement is just like Portland cement. It's pneumatically handled after it's ground into silos and into trucks and into the ready mix plants or precast plants. I said it's almost all glass, and you may have a bit of crystalline material in it because it depends on how quickly it gets granulated or how much water they're using, but generally it's 90% to 100% glass. It doesn't have to be 100% glass to be very reactive. And as I mentioned, because of its composition, it's got a lot of lime and calcium oxide in it from the fluxing stone, 35 or 40%, which is not as, it's getting close to Portland cement, which has about 60% lime in it. But it won't, because of that composition, it won't form a glass naturally. So you have to fool it by quenching it rapidly into a glass. So that's why the granulation process is required. And this is just some data on some old German data showing strength of mortars versus glass content of a slag. So the higher slag glass contents, the higher the strength. But you can see that it's between 80 and 100%. There's almost no difference. And so air-cooled slag would be down at this other end. This is just a grain, a typical grain of slag glass after fracture. And because it's a glass, you may or may not be familiar with X-ray diffraction, but typically X-ray diffraction will pick up peaks due to specific planes of minerals that are present, but glass doesn't because there's no regular order to a glass. So this big hump in the background is due to the glass material. There's a tiny bit of crystalline material here, which has been quantified here using, this is about 96% glass, the rest are very small amounts of minerals in this glass. And as I mentioned, the composition of slag, the blast furnace slag, is shown in this light blue circle, is much closer to Portland cement than a Class C ash and a lot different than a Class F ash. And most natural pozzolans are aluminosilicates. Over here, silica fumes up at the top. It's almost pure silica. But the material that's closest to Portland cement is slag. And ground limestone, of course, is just pure calcium carbonate, which would be over here on this end. Now, I mentioned that slag composition is quite consistent in North America or in any given area of production because they're typically using similar ores and fluxing materials. The composition is similar. So the different colors here are showing countries that produce blast furnace slag. And North American slags typically have low alumina contents, which is the light blue, low alumina, medium calcium to silica ratio. Whereas, say, South America or Central America, they have higher alumina contents. And Asian countries have very high alumina contents, China, Korea, Japan, for example, and Australia and South Africa. And so that has some impact on whether they intergrind calcium sulfate in the slag in it. But from a given source, it's very consistent. So North America, especially the US, there's the slags around Chicago and other iron producing areas are using ores that give you this light blue, but there are slags coming into the East Coast and West Coast of the US that are coming from Asia or from Europe. And so they have to treat them a bit differently, but you end up with the same product. There's a specification for slag cement. It's the ASTM C989. And it has, again, as I said, the main thing that they can control the strength activity is the fineness. So they control the oversize on a 45 micron sieve or 325 mesh sieve, and they measure the blade air permeability, although there's no requirement for that. And there's different strength activity levels. In the ASTM standard, there's 3 strength activity levels, grade 80, 100, and 120, based on strength of mortar cubes at a 50% replacement of cement relative to the straight Portland cement control mix. And the only limit on chemical limit is sulfide sulfur, because the sulfur in blast furnaces in a reduced state are sulfide sulfur, and they limit that to 2.5%, but most times it's typically under 1%. Now the sulfide sulfur, though, because it's reduced, can cause a green color due to iron sulfide or calcium sulfide that forms in the fresh concrete, and you can get a greenish tinge on the surface of the concrete or on the interior of the concrete, but typically this rapidly disappears after a few hours or days and turns due to oxidation of that reduced material, and the final result is a concrete with almost white color. It's almost like using white cement. So it's a much lighter color than straight Portland cement concrete. However, if you cast fresh concrete into, submerge it in water and leave it underwater, that green color may persist. Swimming pools are an example where they immediately fill the fresh concrete after set the pool up. It may not whiten, but that's an unusual situation. And again, they may add intergrind calcium sulfate to optimize performance, especially with higher alumina slags that are coming from offshore. Slag can also be used as blended cements. And ASTM has a standard, 2 standards for blended cements. One of them is C595, which is prescriptive, and there's 2 levels of slag for 1S for less than 70% slag in the blend with Portland, and 1S with greater than 70% slag. 1157 is a performance specification, and they have the different classifications based on what you're using for: general use, higherly strength, moderate heat, moderate sulfate, low heat, high sulfate. Regardless, for the 595 less than 70% slag and 1157 GU cement, the set times and strike development curves are very similar to those in the C150 spec for Portland cement. In fact, in some cases, they're higher for the early strengths than with Portland cement. So the performance is very similar to Portland cement. Carrying on, Chapter 5 talks about proportioning concrete with slag cement and use with chemical admixtures. I'll mention a few things. The batching, and this is right out of the document, is very similar to patching ordinary Portland cement concrete. You typically batch the slag cement after the Portland cement in the same way hopper, and they're mixing, and the mixing time is the same regardless of the slag. In terms of placing, you want to make sure the concrete's placed regardless of what's in it. Slag typically helps the viscosity or the fluidity of the concrete and enhances the consolidation and pumping of concrete. Even if the slump doesn't change, often it's easier to pump. And if you want more information, I've included the link to the Slag Cement Association website here. Influence of chemical admixtures is similar to with Portland cement concrete, although like just when you change Portland cements, you're going to change dose rates. The same with the different amounts of slag, you're going to change dose rates, or may have to in some cases. Air entrainment is not like fly ash. The air entrainment capability with slag cement should be very similar to Portland cement. It doesn't stifle air entrainment. And it can be used in ternary blends. You can mix slag with fly ash and Portland cement, or slag and silica fume together, and can be used with limestone as well. So you can take a 1L cement and mix slag with it. And actually, it's interesting, the 1L cements with slag work better than the type 1 with slag. And I'll talk about fresh properties. I won't go through all of this, but I'll talk about some of the items here. If you want more information, you can read the 233 document. The set times may change. Of course, temperature has a big impact on it. Even with Portland cement here, temperature going from 90 Fahrenheit to 73 to 50, the set time goes up as it gets colder. Same thing happens with slag, and there's data here for 30% and 50% slag cement replacing Portland cement. At 30%, the changes are very minimal, at 50%, you get a bigger effect, especially on the at cold temperatures. So it may involve adjusting proportions with different weather or temperature conditions. The other issue is that typically you get less slump loss at the extreme edges of temperatures here with slag. In terms of saw cutting, it's similar. There might be a slight delay in saw cutting joints, especially in cold temperatures. And you may, in some cases, they may reduce the amount of slag used at cold temperatures to allow saw cutting within a certain window. As a rough guide, the time to saw cut is delayed about 30 minutes for every 10% slag replacement in the mixture. And that may be made worse by lower temperatures. Again, there's more information on the website about this. So hardened properties, and these figures are out of the document as well. These are actually mortar cubes, 2-inch mortar cubes at different ages for different slag contents. And you can see that for 1-day strengths, the slag is a little slower than Portland cement. You get a reduction in 1-day strength as you add more slag. And at 3 days, a similar effect. But by 7 days, the effect is either neutral or better. And at 28 days, up to 50% slag, it continues to get better and beyond to 1 year here. At 65%, you're still better than the straight Portland cement, but it's beyond the optimum, if you like. 50%, if you want high strength, would be about the optimum. But if you're still getting way better strength than the Portland cement here at an equivalent age with the higher slag contents. And typically, if you're using mass concrete and trying to reduce heat of hydration, you'll be over in the 65 or higher range. Now, these are concrete strengths for 40, 50, and 65% slag replacement of cement. And the solid circles here are the straight Portland here. And what you can see is after 7 days, the slag concretes exceed the strength of the Portland cement concrete. Beyond, even at 7, they're higher, and at 28, they're much higher. Whereas at early ages, 3 days and 1 day, they may be lower. And again, with flexural strength, the flexural strength is higher by 28 days than with Portland cement concrete. And that can be an advantage for pavements. And here's some more data for a given concrete. The top series of data is 611 pounds per cubic meter of cementitious material, and it shows the 7-day strength, a little lower with higher slag, 50% slag, but higher strengths at 28 days. And the bottom chart here is for flexural strengths, and you get better flexural strengths at 7 and 28 days with 50% slag than with Portland cement. Drying shrinkage, this is some of my own data, but so equivalent concrete's a 0.55 water binder ratio, 500 pounds per cubic yard, with a 3/4 inch aggregate. 7-day moist cured and then drying at 50% humidity as per ASTM 157. And you can see that there's less shrinkage with the slag here as you increase the amount of slag. Now, these were low alumina slags. High alumina slags, some of the Asian slags may show a different trend, but if they add the gypsum to the, when they intergrind those high alumina slags, they will get reduced shrinkage as well. And this has to do with optimizing the sulfate in the pole binder. Okay, I want to talk about permeability and pore structure. So again, the slag forms more calcium silicate hydrates, which fills in pore space. And it happens later, so it subdivides the original pores that the Portland cement sets up, and it helps reduce the permeability of the concrete, also strengthens these aggregate interfaces. That happens to be a calcium hydroxide crystal sitting on a bed of calcium silicate hydrates. And this is just some pore size distribution. So there's a volume of pores on the vertical axis. Pores getting smaller as you go right here. And I've just picked one bar at 50 angstroms, which is 500 nanometers, which is 0.5 of a micron. And you can see that with the slag cement here, 40% slag, there's way fewer pores with big pores here than with the Portland cement mix. And those big pores are what increases permeability. So having fewer of these big pores reduces the permeability of the concrete. These are concrete data now. So again, some of my own work from 20 years ago, showing a 35% slag mix versus a Portland mix for a 0.4 water binder ratio, fixed water content, and the slag mix is in red here. And if you measure it 1 or 2 days, the slag isn't as it's more permeable than the Portland cement mix, but by 3 days they're both the same. By 7 days they've crossed over, and by a month and a half the slag is an order of magnitude. That's a log scale here. So that's 10 times better reduced permeability at a month and a half than the Portland cement mix. These are chloride ingress on some cores taken out of 2-year-old concretes made with different cementing materials, and we measured the ASTM 1556, essentially the chloride ingress test, and measure these are chloride profiles after 40 days exposure to salt solution, going in from the surface on the left, moving in, and so half an inch is here at about 12.5 millimeters. And so you can see the Portland cement mix, the chlorides have gone in a lot further. A 35% slag mix, a lot less. The silica fume mix here, it's 8% silica fume is less, but a 35 slag and 5 silica fume mix is even better. So the slag does a lot of the work here in reducing the chloride ingress. Again, on permeability, this is the STM 1202 rapid chloride permeability test. So these really old concretes with 0, 25, and 50% slag, same water content, same water binder ratio. Strengths are similar, not exactly the same, but very similar because they're starting at the same porosity due to the equal water content. But there's a 5 times reduction in the water or chloride permeability by 1202, and for water permeability, almost the same amount of reduction. So you're showing the benefit of adding slag, all other things being equal. And again, this is more ASTM 1202 rapid chloride data from Mike Thomas at University of New Brunswick, showing changes for 0.5 concretes at different ages ranging from 3 days to 2 years here, and showing their big reduction with 50% slag. The crossover here again is just after about 7 to 10 days, and then after that the slags keep getting better and better, and the Portland cement not so much, because the slag continues to hydrate for a longer period than the Portland cement. And this is actually seawater exposure from Treat Island, again from Mike Thomas's data. So seawater exposure after 25 years, showing concretes at equal water binder ratio but different levels of slag. And again, you see the same. The Portland cement mix, the circles here, has penetrated a lot further. In fact, it's even at 90 millimeters depth, it's way beyond the amount of chloride you need to cause corrosion of steel. Whereas 25% slag protected down to about 50 millimeters, 45% slag protected down to about 40 millimeters, and 65% slag protected down to about 30 millimeters at a point where you'd start to get corrosion. I mentioned that a slag will reduce the heat of hydration. These are heat curves in a laboratory in a calorimeter. You're keeping the temperature constant and measuring the amount of heat released from the concrete, and showing a Portland cement mix, the solid line on top, and then different amounts of slag. As you increase the slag, you get reductions in the heat of hydration at these early ages, but they do carry on longer at later ages. And slag is used a lot in mass foundations. This happens to be an example near me in Ontario at what is now a CRH cement plant. They put in a vertical roller mill 15 years ago, and it was a mass foundation, 14 by 14 by 5 meters thick. Sorry, whatever 5 meters is, about 16 feet thick is the minimum dimension. And they use 50% slag and 50% of a type 1 cement. Had to meet freezing requirements. It had to be about 4,500 psi, 0.45 water binder ratio, and air entrained. So they did that with 50% slag. And these are the temperature curves. They measured the temperature in the foundations. This is at the center of the foundation. The maximum temperature got to 61 Celsius or 142 Fahrenheit, and the bottom of the foundation here and the top, with the top's the purple, the bottom is the green. The maximum differential here is about 43 Fahrenheit. And if they'd used higher slag or larger diameter coarse aggregate, they could have reduced that further, because they were trying to avoid thermal cracking in this big base. And it just shows the strengths they got. 1,000 psi at 1 day, 4,000 at 7 days, 6,000 at 28 days. And they got pretty low shrinkage. Anything below about 0.04% here would be considered low shrinkage. And under 1,000 coulombs at 56 days. There's some data from Virginia on the I-895. Again, massive footings and columns. I'm sorry, this is only in metric. But again, 35 MPa is about 4,500, 55,000 psi. 75% slag and a moderate heat cement. And these are the sort of temperatures they were getting. About 54 Fahrenheit or Celsius was the maximum. The surface got up to 45, so the maximum differential at any point, this is over about 2 weeks here, was 15 Celsius, which is about what, 22, 23 Fahrenheit. And this is the strength development curve with 75% slag. They were getting the required design strength at the 28-day design strength. They got it at 15 days, even with 75% slag. Of course, when the concrete gets hot, that'll accelerate the strength gain of the slag concretes. So you'll get a big difference in what you get in a structure versus what you get in a laboratory at constant temperature. You actually get better strength development in a structure than in the lab. This is a more recent structure, a cable stay bridge in St. Louis. And it shows the base on the left here of this heavily reinforced support structure for the cable stay, and then shows with the pylon going up further. There's a 6,500 psi spec, and they actually got 8,000 psi at 2 months. 70% slag used there. Maximum temperature was 119 Fahrenheit. They wanted it below 150, so they got a way less than that with 70% slag, and the differential was well under the specified 35 max. And because the slag actually developed strength better and kept the temperatures down, they actually could save on the curing cycle, because they didn't have to protect it from thermal gradients as long. So they were able to save a lot of time in the construction because of slag cement here. So I'll talk about some of the durability properties. These are discussed in Chapter 7 of the 233R document. Slag, as I said earlier, slag cement can improve sulfate resistance. This is data. These are mortar bars, the ASTM C1012 mortar bars, which is the standard test for evaluating sulfate resistance of concrete with SEMs. A straight Portland cement, it's a type 1 cement with almost 12% C3A on it. Within a couple of months, it's failed. The failure criteria is typically taken at 0.1% expansion at a year, and with the same cement replaced with 40, 50, or 65% slag, the expansions are way lower. And if they got to 50, even after 10 years here, they never reached the 0.1% criteria. So you can use a high C3A type 1 cement with slag to get equivalent to a sulfate resistant binder. At the same time we did that work a long time ago, we also cast concrete. We published this in the ACI Materials Journal in 2016. These are concretes we cast, concrete cylinders, and we put them in two different sulfate environments here, 3,000 ppm or milligrams per liter sodium sulfate solution, another one in 50,000, which is the same as the C1012 test. This is again that same 12% C3A cement with 65% slag at 0.45 water binder ratio. There's no damage in either case to the slag mix after 38 years. This is a type 5 cement, and you can see there's cracking here. and a lot of damage in the higher strength solution. This is a type 2 cement, 7% C3A, and again, it's showing more damage than the type 5 cement, but the slag cement with the high C3A type 1 cement is performing way better than both those after 38 years. Alkali silica reaction, there's a lot of data on the benefits of slag on alkali silica reaction. I was involved with an exposure site that we cast in Ontario with our very reactive aggregate, the Sprat aggregate, back in 1991. We've now got 27-year data on that, and with 6 different concrete mixtures, same water binder ratio, same binder content, but different cementing materials, including slag mixes. And I'll just show you one set of data from some of those beams that were in the background. We go back to the picture here. We cast pavement slabs, we cast unreinforced and reinforced beams, and the beams were 2 foot by 2 foot by 6 foot. These are the unreinforced beams, and they're exposed outdoors. And this is data up to 20 years. The high alkali cement started to crack, expanded and cracked after only 5 years in the exposure, and kept expanding and still expanding after 20 years. We use a low alkali Portland cement, also cracked up after about 10 years, and it's still expanding after 20. Now we use 25% slag with the high alkali cement. It slowed things down, but not 25% slag wasn't enough. 18% of a class F fly ash also wasn't enough. We knew that at the time, but we ran out of fly ash at the trial. And this is a silica fume slag mixture, 25 slag with a bit of silica fume in it. And it's not expanding after 20 years. And here's a 50% slag with the high alkali cement. And after 20 years, it still hasn't expanded at all after 20 years. And it's the same after 27 years. I just didn't get the data to graph for this. So it's been very effective at reducing that expansion. We actually built a dam in Ontario, several dams in northern Ontario near Lake Superior back in the mid-80s. And with 50% slag with a known reactive aggregate. And after 30 years, there's still no cracks in that concrete. There's no signs of it petrographically. I've got to get some more cores and check it, but there were no signs 15 years ago. The highway department built a highway bridge from the same ready mix plant using the same cement and the same aggregate for a highway bridge, and it cracked up well before 15 years. They didn't use slag, but on the dam they used slag, and there's no cracking. Now this is a somewhat outdated map. Apparently the SCA has new data, but it hasn't been graphed yet. And it shows the maximum amount of slag allowed in different state by different state DOTs. So the dark greens are above 50%, so Florida, California. 50% of the medium greens, and then 35 to 49% of these Iowa, Minnesota greens. 20 to 34% are the lighter greens, which would be these guys, Mississippi, Arkansas, Ohio, New York. And out in the Midwest, or the West, I guess, it's not specified because there wasn't slag available in those marketplaces at the time. Because a lot of the slags are either in the Great Lakes region or around the coastline or up the Mississippi. And the reason there's limits on the maximum amount of slag here is mainly due to concerns with de-icer salt scaling. You can see that the states that have less concern with de-icing at all have higher amounts of slag allowed. And part of the problem here is the ASTM de-icer salt scaling test, the 672 test, is very severe on non-Portland cement concretes because of the curing regime they use and the finishing regime used in the test. In the field, slag performs a lot better than that. This is some concretes we cast, pavement sections exposed to salt and freezing and snow removal after 10 years, and it shows these are all 50% slag mixes with two different curing regimes. They were moist cured for 7 days or cured with a curing compound. We tried to prematurely finishing because the finishing time was a little slower for these mixes, so we had them prematurely finish the concretes, which could trap bleed water. So the curing compound or moist curing. And what you can see is with the curing compound and normal finishing, there's absolutely no scaling. There's a slight, with the moisture and has few sand grains exposed, a little more exposed with the early finishing because they trap some bleed water. But generally, after 10 years, that's in excellent condition. And this is seeing a lot of high truck traffic. In Delaware, here's some pavements that are 10 years old. They use both 35 and 50% slag. And you can still see the tine marks after 10 years on these concretes. There's no scaling observed for these pavements in Delaware. Here's in Michigan, a 5-year-old multi-lane, multi-span bridge deck with 30% slag, and there's no scaling observed. Again, you can see the tine marks, the lateral tine marks on the pavement. Now, slag is used in all sorts of applications, and I'm not going to talk about all of these. I'll just show a few examples. It's used in all ready-mixed concrete. It's used in concrete products, pavers and block. Used in mortars and grouts, in CLSM, environmental structures because of the sulfate requirements, high-strength, high-performance concrete, and I'll show a few examples, industrial floors, and all kinds of examples as shown on the right. And if you want to see more, you can read the 233 document. I'll just give you a couple of, this is a recent example from the I-96 reconstruction in Michigan, 7 miles of full-depth 8-lane replacement, and 37 bridge structures rehabbed or replaced. And again, they used greater than 30% slag because they were worried about alkali silica reaction, as well as scaling and freezing and salt. And they had no problem with that, and it helped with the lighting because of the light. They put in new LED lighting, and with the lighter slag pavement, they needed less light intensity to light the road at night. JFK, they redid one of the runways there with an 18-inch concrete overlay, and they widened it from 150 to 200 feet wide and put an extension on the runway 5 years ago. They used 40% slag, a blended cement with 40% slag, the maximum 550 pound per cubic yard cementitious material. They wanted low permeability, high flexural strength, and so they exceeded that. They got almost double the required minimum flexural strength for that pavement with the slag mix. And again, there's many other examples. Those two examples are on the SCA website, but there's many other examples of slag in pavements and in airport structures. I mentioned ternary mixes. In Ontario, we use ternary mixes a lot. Anytime where silica fume's been used for the last 25 years or 35 years, slag cement has always been added to improve concrete durability and improve constructability. One of the reasons that is a lot of the problems with when silica fume was first adopted, it caused a lot of stickiness. It was difficult to use the paving machines. Finishers didn't like it as much, but putting the slag in with the silica fume, using 6 or 7% silica fume and about 25 or more 35% slag, took away that stickiness, improved the flowability of the concrete, and made the finishing easier. And because of that, it also reduced, a lot of the stickiness was coming from the high doses of high-range water reducer, and the slag helped reduce the required dose, which again helped reduce the stickiness. The slag reduced the early heat of hydration, especially for these high-strength mixes they were casting. They were casting up to 14,000 psi concrete, and they're getting high heats of hydration, so they wanted the slag to help reduce that. And it continues to improve the strength and chloride resistance beyond 28 days. Silica fume reacts very quickly, but by 28 days, it's pretty much done its thing, whereas slag continues to improve the concrete, both in terms of strength and chloride permeability, well beyond 28 days. And ternary mixes with fly ash also work. They've used a lot of that. I know in Ohio, slag ternaries with fly ash, other areas, and you can use it with limestone as well. That we use it on high performance, use 100-year service life tunnel liners, such as one ring of a tunnel liner, 7-segment precast tunnel liners. They were cast with slag and silica fume quite a few years ago now, almost 25 years ago. And again, they use a blended silica fume cement with about 8% silica fume in it. They used about 30% slag here, 0.31 water binder ratio. They're getting 75 MPa, which is about 11,000 psi at 28 days. Low chloride diffusion rates, low water permeability rates. The Coulomb values were between 100 and 500 from that work. Again, just another local Toronto example. Of course, like every airport in the world, they're always under construction. The Toronto one was rebuilt around 2000, and they initially tried 4 bridge decks using a blended silica fume cement with 25% slag for what they wanted for high performance bridges in terms of chloride resistance. And they placed it in cold weather with large pours, 16-hour placements, continuous placements on these long bridge segments, up to 1,200 cubic meters in a single pour. And it was so successful, they did all the 40 bridge structures, including the arrivals and departures decks, with slag concrete as well. And the parking garage as well. The huge parking garage was all built with slag cement. And again, here's some data from that first bridge deck they did. Got a fairly high slump, 7-inch slump, almost 7% air with a good spacing factor. That's 0.008 here inches. Strength was about 7,300 psi with a fairly low standard deviation. Again, about 600 Coulomb values and low chloride diffusion rates, which is what they're looking for, long service life with low maintenance. And I know the airport has done a lot of 10-year and 20-year inspections of these bridges, and there's no evidence of any corrosion on these bridge decks. Again, a view of one of the departure decks being placed here, multiple pumps, and a whole bunch of pumps on one of the other bridge decks. And that's the new terminal there. That's the big parking garage when it was still under construction, all these bridge decks. And this terminal was later demolished. And that was all used as our recycled concrete aggregate for all the new runways and taxiways. But anyway, all this concrete had slag and silica fume. The parking garage just had slag. One other example of a ternary mix for a parking deck, again going back over 20 years, fairly large pour with a blended silica fume cement and 30% slag. It was done in early July, and it was like it was in the 90s, well into the 90-degree Fahrenheit. There was a wind blowing, it was sunny, so all the things you need for plastic shrinkage cracking. But they pumped this concrete. They had 3 separate pump setups, 3 finishing crews, a low water cement ratio because it was supposed to be a large parking deck for a transit infrastructure. And they were getting 45 megapascals, which is 7,000 psi, 6,000 psi, and they fog misted the deck to avoid the plastic shrinkage even in those extreme situations. And they didn't get any plastic shrinkage cracking. And the Coulomb values at 2 months were under 200, and again, low chloride diffusion rates. Now, the last chapter in the document is on sustainable development, and there's a link there to the Slag Cement Association section on sustainability. So there's some sustainability benefits from using slag. It's a recovered material from the iron process, reduces the amount of cement required, which reduces the embodied energy of concrete, reduces the embodied greenhouse gas in concrete, decreases the use of virgin materials. In other words, they don't have to mine as much material to make cement clinker. Because of the lighter color, you reduce the urban heat island effect because the higher reflectivity of the concrete reduces temperature rise in hot weather. And you're increasing the structural life by improving the durability to all these aggressive things like chlorides and sulfates and cracking due to thermal stresses. And avoids disposal of slag, which is beneficially utilized. And this is some data from the document, just one table, shows a couple of examples of different types of concrete with different levels of slag. And this is the life cycle inventory savings that are listed there in terms of life cycle reduction in energy, reduction in emissions, and reduction in materials required for different applications. So pretty substantial reductions in energy required for the life of the structure. Okay, now the guide, that's the picture of the guide on the right. You can search it on the website. It's listed under standards and documents. It last was updated in 2017. I was the chair of the committee at the time it was revised. And lastly, I plugged the Slag Cement Association website. It's a very useful website. It's got a lot of information, statistics on slag use, where different examples of its use, how it affects concrete in different ways, and you can get it at slagcement.org. So at this point, I think the timing's about right. We've got 5 or 6 minutes left for questions, so be happy to answer any questions if you have some.
Great. Thank you, Doug, for taking the time to do today's presentation, and we would like to jump into the questions. Our first question is, are there any issues adding non-metallic fiber mesh to a high percentage slag concrete mixture?
I don't have any direct experience, but I don't see why there would be a concern. The non-metallic fibers aren't going to react any differently with slag cement than they would with Portland cement. So I can't see any detrimental effect of using slag cement. I imagine the benefits are similar.
Our next question is sort of a two-part question in a way. Can slag cement be blended with high early strength Portland cements, such as like a type 3, to help improve the slow strength gain of slag cement? And can it be used with any type of Portland cement, or are there any limitations?
It can be, slag cement can be used with any type of Portland cement. It has, I think, to me, the strongest benefits from use from a high alkali, high C3A cement, because the alkalis help the slag activate the slag. So a low alkali cement may not be as beneficial as a high alkali cement to mix with slag. But it can be used pretty much with any type of, I've used slag with type 2 cements, with type 5 cements. I've not done it with type 3, but some of the precasters use a type 3 cement and slag, sometimes slag and silica fume together. With precasters, they're typically looking for really high area strength as opposed to compensating for low strength. But as I mentioned, I think you can redesign the mix a little bit to compensate for any low strength you get with higher slag replacements. And the other issue is that in a structure, other than a very thin, like a suspended slab, typically you're going to get a temperature rise in a column or a wall that will accelerate the strength gain of the slag concretes. Slag is a lot more sensitive to temperature than Portland cement. In other words, the benefits of increasing the temperature are much higher with slag. And so when this temperature goes up, the strength gain goes way up.
Doug, you showed some different applications, and the next question is sort of regarding that. Is there any inconvenience using slag cement in a sprayed concrete, such as like a shotcrete application?
Good question. I'm not aware of any downsides. Usually with shotcrete, the issue is rebound. And you want to use a system that gives you less rebound. One of the reasons they typically like silica fume in shotcrete. I'm not sure how slag would, there may be, I'm sure there's people that do know the answer. I don't have the answer for that question.
Okay.
But it certainly would help compact, it'd be easier to compact that concrete when it is impacting on the surface with slag.
Different question. Do you recommend designers specify blended cement mixtures using slag that perhaps they modify their concrete strength test requirement from 28 days to 56 days to give that slag an opportunity to perform?
Yeah, well, that's an interesting point. If you're trying to, if your concern is durability, like if you're looking for reduced chloride ingress, then 56 days has a lot of advantages. Our Canadian standard has a 1,000 coulomb requirement for high performance concrete, but it's at 91 days actually. And for regular concrete exposed to like chlorides and freezing, it's 1,500 coulombs at 91 days. The reason is to allow SCM such as slag to develop their potential before you take the measurement. If you're building a structure to be resistant to chlorides for 50 or 100 years, then an extra month isn't the big deal here. And so, yeah, later ages are more beneficial from the durability properties because these materials don't necessarily develop their properties at the same rate as Portland cement. All our 28-day requirements are based on Portland cement.
Doug, earlier in the presentation, you were mentioning that slag hydrates for a longer period than Portland cement, and that this is beneficial for permeability. The question is, can you explain a little bit about why does it continue to have the hydration process last longer?
Yeah, and I may have not said that correctly. Portland cement continues to hydrate as well, but the impact of that extra hydration is smaller at later ages. With slag, because it's slow reacting, because of the lower calcium to silica ratio in the slag, it reacts more slowly. But when it does hydrate, because of that, it incorporates more alkalis into the hydrate, and it continues that for a longer period of time. It's just more slowly soluble. I mean, Portland cement isn't totally soluble in water. It's not like instant coffee. It doesn't dissolve in your water immediately. Some of it, the surfaces dissolve first. And it turns out that with slag, that dissolution rate is lower than Portland cement.
All right, Doug, we do have one last question for this afternoon. Our question is, why would you want to use slag cement over a fly ash as a supplementary cementitious material in placing exterior concrete pavement exposed to freezing and thawing and thermal expansion environments?
Well, a lot of what you use, whether it's fly ash or slag, depends on what's available in the marketplace. And also, as I mentioned, slag doesn't have a negative impact on the air entraining dosage required to get a consistent air content and get the right bubble size distribution for frost resistance. Whereas fly ashes can be somewhat variable depending on their carbon content, especially with powder activated carbons being added to reduce mercury in the fly ash or in the airstreams from coal power plants. So, and again, the slag is more controlled, whereas this thing is more variability in the fly ash. But both can be done. It's a matter of controlling things and keeping on top of it.
All right, Doug, thank you again so much for your time this afternoon, and shout out to the Slag Cement Association and Drew for supporting today's webinar as well. Topics for upcoming live webinars are shown on your screen and in your handout. ACI does offer many learning opportunities. Please check out more of our offerings at aciuniversity.com. That does conclude today's webinar presentation. We hope you enjoyed it. Thank you for joining us.